I just read something that completely changed how I think about AI, and I had to share it with you. Scientists put language models like GPT-4 in competitive situations where they could talk to each other. And guess what happened? They slowly learned to cooperate completely on their own. Nobody programmed them to work together. They just figured it out through chatting. In one research example, this could save lives, but in another, it resulted in AIs price fixing and forming cartels. I'm Evan Goldstein. I'm a licensed professional engineer and a data scientist. I'm building AI Capitalist to talk to the leaders and the thinkers, like you, about navigating this new world of thinking machines. Okay, picture this. You're playing a game with people that you've never met before. Everyone's trying to win, right? That's the whole point. But then something weird happens. These total strangers start helping each other out, and they do it without even talking about it first. They just naturally form these little alliances that somehow make things better for everyone. I always thought that kind of coordination needed some special human touch. Reading the room, picking up on social cues. But AI systems can do this too. So I just read a paper called Shall We Team Up? Love the title, by the way. And the researchers found that AIs are doing this too. These large language models, like GPT-4, can actually learn to work together in competitive situations without anyone telling them to. Nobody programmed them to cooperate. They just figured it out on their own. And what really got me was how they did it gradually through interaction, kind of like how we humans learn to play nice with others. So the AI systems are making more and more decisions in our everyday lives, from what prices we see online to how our resources get managed. And if these systems can decide on their own to team up, could they potentially collude in ways that nobody intended? Like, what if pricing algorithms from different companies secretly learn to fix prices together, or if AI systems find sneaky ways to cooperate that fly completely under their human supervisor's radar? I'm not saying we should panic, but these questions are definitely worth asking. So let's dig into what these researchers actually found, because the rabbit hole goes deep. The first scenario was the Keynesian beauty contest, a classic game from economics named after John Maynard Keynes. In this game, multiple players, in this case 24 large language models, each choose a number between 0 and 100. The winner is the player whose number is closest to 2/3 of the average of all numbers chosen. Now, this creates a complex strategic puzzle. Well, if all players chose randomly, which would average out around 50, the winning number would be about 33, which is 2/3 of 50. But if everyone realizes this and chooses 33, then the winning number would be about 22, which is 2/3 of 33. And if everyone realizes this second level reasoning and chooses 22, then the winning number would be about 15, and so on. Now, a fully rational player would continue this logic until reaching 0, but human players rarely go that far in their reasoning. The key insight is that winning requires accurately predicting what others will do. This is why cooperation can be valuable. If players can agree on which numbers to choose, they could all win together instead of competing against each other. The researchers allowed these agents to communicate with each other for varying numbers of rounds before making their final choice, to see if this sort of cooperation would emerge through discussion. Now, figure 3 here illustrates the baseline design in the KBC case study, showing how agents go through K rounds, that's the number of rounds of communication, before planning and choosing their numbers. In the Keynesian beauty contest, the researchers found that as agents engaged in more rounds of communication before choosing their numbers, the variance in their choices decreased significantly. This suggests that through discussion, the agents were converging on similar number choices, a form of implicit cooperation. As shown in figure 4 of the paper, when agents couldn't communicate at all, which is K equals 0, they chose widely varying number. But with just one round of communications, and especially with 3 rounds of communications, as you can see the lines coming together in the graph here, they often converged on the same strategy. Now, by coordinating on the same number, multiple agents could win simultaneously and then share the prize, which created a better outcome for the group than if they all competed individually with different numbers. This coordination wasn't random. The communication logs revealed that the agents were actively discussing strategy and reaching consensus through phrases like, quote, "let's move forward with the lower number strategy," and, quote, "I agree with the group's consensus." And in figure 5, compares the distribution of players' choices in the simulation against results from a large-scale New York Times experiment, showing remarkable similarity in how large language model agents and humans approach this problem. Importantly, when researchers explicitly instructed agents to cooperate, they immediately chose the same numbers after just one round of communication. So look here, you're seeing these spikes in the New York Times responses with humans. Somehow the AI, when initially selecting at the same spikes as humans did. It's not quite clear, to me at least, why this happened. So in contrast, the baseline scenario showed a gradual convergence over multiple rounds of communication. And this difference suggests that the cooperation observed in the baseline was genuinely spontaneous and that it emerged naturally from the agent's interactions rather than being pre-programmed into their behavior. So the question that the researchers were asked, which is, would agents spontaneously collaborate, challenges a common practice in AI agent simulations. Typically, when researchers want to study how AI agents behave in social scenarios, they provide detailed instructions that guide the agent's behaviors. For example, they might explicitly tell one agent to be cooperative or to try to negotiate. But the research team questioned whether these explicit instructions were always necessary. They asked, what if we just place these agents in a scenario and let them figure out strategies on their own through interaction and communication? The researchers also wanted to understand the reasoning process behind any cooperation that might emerge. Was the cooperation a result of the LLMs just applying pre-programmed cooperative behaviors? Or were they genuinely learning to cooperate through their interactions? In other words, were the agents truly engaging in deliberate reasoning based on the context of their situation? Or were they just following patterns that they'd been trained on? All right, so the second scenario was the Bertrand competition. This is an economic model where two firms compete by setting prices for their products. If both prices keep prices high, they can both make good profits, similar to how a cartel works. Yes, everyone's minds go to the Colombian drug cartels, but I assure you this happens in free market economies that are unregulated as well. But each firm is individually incentivized to undercut the others. Now, in a free market situation, each firm is individually incentivized to undercut the other's price to steal customers, which can lead to a race to the bottom where neither company makes much profit. The researchers wanted to see if large language model agents representing competing firms would discover the benefits of keeping prices high, even without being told to cooperate. This is similar to two gas stations across the street from each other. They could keep the prices high and both make good profits, or they could start undercutting each other until neither is making much money. Now, figure 2 here shows the workflow in all three case studies, illustrating how the framework manages LLM agents during simulations, with phases progressing from communication to planning to action to update. So in the Bertrand competition scenario, the results were even more striking. Now, figure 6 here in the paper shows the price trajectories over time under different conditions. Without communications, which is figure 6a, the two firms initially engaged in price competition, but after about 400 rounds, they stabilized their prices around a level that was above the competitive equilibrium. This is a phenomenon known as tacit collusion. It means that even without talking to each other, large language model agents representing competing firms learned to keep prices higher at the competitive level, benefiting both firms at the expense of consumers. And figure 7 compares the first 200 rounds of simulations with default settings versus those with encouraged cooperation, showing how explicit encouragement leads to faster and more stable price coordination. And the other thing you can see here is the volatility, that there's a lot of back and forth while they home in on these final prices. Now, when communication was allowed in figure 6b, cooperation emerged much faster and more explicitly. The agents discussed pricing strategies and agreed to raise prices, eventually reaching levels that were very close to what economists would call the cartel price, the price that maximizes joint profits as if they were a single monopoly. That would be the top line on that graph. The researchers found direct evidence of collusion in the communication logs with agents, and agents were making statements like, quote, "We can both maximize our profit by exploring different price points while maintaining a reasonable price difference," end quote. Now, to verify that this cooperation was truly emerging from communication and not from some pre-existing tendency, the researchers conducted a clever test. They ran a simulation where firms communicated for 400 rounds and then stopped communicating for 200 rounds. And you can see this in figure 6C. What's interesting is that after communication stopped, the prices drifted a little bit back downward toward the levels that were seen in the no communication scenarios, confirming that higher prices were indeed a result of communication between agents. Now, the third scenario that they looked at was the emergency evacuation, which is a behavioral science simulation where 100 agents needed to escape from a room with 3 exits. So now the researchers conducted a clever test. They ran a simulation where firms communicated for 400 rounds and then stopped communicating for 200 rounds, which is shown here in figure 6C. What's interesting is that after communication stopped, prices drifted back down toward the levels not seen in the no communication scenario. And this confirmed that the higher prices were actually a result of the communication between agents. Now, the third scenario was an emergency evacuation scenario. This is a behavioral science simulation where 100 agents needed to escape from a simulated room with 3 exits. In this scenario, if everyone just rushes to the nearest exit, congestion occurs and fewer people escape quickly. But if agents share information and coordinate their actions, more people can escape in less time. This is basically a simulated stampede for the exits in a burning theater. The researchers wanted to see if large language model agents would spontaneously share helpful information and encourage others, even when primarily focused on their own escape. It's like what happens when a real emergency occurs. People can either panic and push towards the exits, which often causes dangerous stampedes, or they can maintain order and help guide each other to different exits for a more efficient evacuation. Figure 8 provides an overview of the grid environment used in the study, with dots representing agents and the progression of evacuation over a multiple round. In the emergency evacuation scenario, the researchers compared evacuation outcomes with and without communication between agents. Now, as we can see, what the researchers found was that agents who could communicate escaped more quickly on average, with all the agents successfully escaping within 50 rounds in every simulation run. The distribution of agents across different exits was also more balanced when the communication was allowed, which you can see in this figure 9 that I'm showing here. This suggests that agents were sharing information about exit conditions and they were guiding each other to less congested exits. Now, in this figure 16, we see the cumulative counts of agents evacuating from each exit under different initial seeds. And this shows that there's a consistency of cooperative behaviors across a lot of different starting conditions. The researchers found examples of cooperative messages in the communication logs, such as bottom exits seem closer with fewer people. Let's choose that for a faster escape. Stay strong and help each other. These messages show that the agents were not only sharing factual information about exit conditions, but also providing encouragement and emotional support to one another, which was sophisticated social behaviors that emerged spontaneously in response to the emergency situation. To make sure that the research findings were solid, the team didn't just run their main experiments, they also set up clever comparison tests. They tried giving some AI agents explicit instructions like, hey, work together, or don't cooperate with anyone. When they compared these results with their original findings, it became clear that the cooperation that they observed wasn't programmed in or due to some built-in bias. It was genuinely emerging on its own AI as the AI agents interacted. Kind of like how you might notice strangers naturally forming lines at busy coffee shops without anyone telling them to do so. The researchers illustrated their core question with a really vivid image that might remind you of situations that you've seen in disaster movies. And I mentioned that earlier with the fire escape scenario. So not all the AI models were equally good at figuring out cooperation. Think of it like different kids in a playground. Some of them naturally learn to share toys and others take longer to get there. GPT-4 consistently showed this cooperative ability across all the tests, but other models like GPT 3.5 and Claude were just not as reliable. This suggests that spontaneous cooperation isn't a simple skill. It's a sophisticated capability that gets better with more advanced AI. It's similar to how you might notice more complex social dynamics among older kids compared to toddlers who are still in the mine phase of development. Like, it's mine, give me. So what does this matter to everyday people like you and me? Let's say you're scrolling through social media, you're checking your email, you're just ordering takeout. Have you ever stopped to think about all the AI that's working on it behind the scenes? This research about AI agents learning to cooperate isn't just a boring academic paper that's going to be gathering dust on a shelf somewhere. It could actually change how technology impacts your everyday life, and probably sooner than you think. You know how sometimes you'll check prices for a flight and then you'll come back later and they're mysteriously higher? You might even try logging on incognito versus from your regular browser with all the cookies and see that there's two different prices quoted. Think about how different online stores end up charging similar prices for the same product. Let's say that all of these AI systems setting those prices started quietly working together without humans telling them to. They could essentially form their own little digital price-fixing cartel, prices artificially high while we are none the wiser. And this could all happen without leaving any obvious evidence. There would be no smoke-filled rooms or secret handshakes, no email trail, no phone logs, just algorithms silently agreeing to maximize profits at your expense. The researchers themselves raised this red flag, saying point blank that these AI systems can learn to collude in marketing environments. They suggested that we might need new rules for AI in financial markets, kind of like how we need lifeguards at the pool, except these lifeguards will be watching for suspicious patterns in how AI systems interact with one another. But it's not all doom and gloom. Cooperative opportunity and cooperative availability could be very helpful in a crisis. Let's say you're facing an approaching hurricane. Instead of every navigation app independently routing everyone down the same evacuation route, hello massive traffic jam, AI systems could work together to spread cars across different routes based on real-time conditions. Or think about smart home devices, your thermostat, your security system, and lighting. They could all learn to cooperate in ways that would make your life easier without you having to program every little interaction. Your morning alarm could trigger a gentle warm-up of the shower, and your coffee maker could get the coffee moving, and your smart speaker could read out today's weather and top news stories, all coordinating without you having to set up a complicated if-then rules for every possible scenario. So let's take a step back and think about this research with a healthy dose of skepticism. As cool as these findings are, they come up with some pretty significant yes, but moments that we shouldn't ignore. The researchers were working with some limitations. First, they mostly used just one version of GPT-4 because running these experiments isn't cheap. It's like testing a new diet on just one person and then claiming it works for everyone. Would we see the same cooperative behavior in other AI models, or even in different versions of GPT-4? The researchers were pretty upfront about this being more of a, hey, look what we found study rather than the final word on AI cooperation. And you know how some people are just naturally helpful? Like, you might have a friend who always offers to drive everyone home after a party. AI models like GPT-4 are actually designed to be helpful and to avoid doing harmful things. So when critics look at these results, they might say, wait a minute, is this really spontaneous cooperation? Or is this just the AI equivalent of being raised to say please and thank you and then acting on that training? The researchers tried to control for this, but it is a fair question. Are these AIs truly figuring out cooperation on their own? Or are they just showing behaviors that they were already designed and inculcated to have? But we also have to be real about the simulations. They're like those perfectly controlled cooking shows where everything goes exactly according to plan. Real life is much messier. It's like practicing parallel parking in an empty parking lot versus doing it on a busy street with impatient drivers honking behind you. Would these cooperative behaviors hold up in the chaotic real world? That's an open question. What's interesting is that other researchers are seeing similar patterns. Some of them have even found that AI agents will divide up markets between them without being told to do so. Kind of like how gas stations on opposite corners somehow end up charging the same prices. There's a growing awareness that AI systems might naturally drift toward these cooperative or collusive behaviors in ways that we hadn't anticipated. The silver lining is that some smart people are already working on safeguards. There's research looking at how to detect and prevent unwanted AI cooperation, like digital hall monitors keeping an eye out for algorithmic whispers between systems. It's a reminder that this technology is really a double-edged sword. The same features that might help AI coordinate emergency evacuations could also enable the price fixing we saw. It's like fire, incredibly useful when controlled, but devastating when it's not. As we put these AI systems into more complex social environments, from online marketplaces to healthcare systems, we need to understand how they might work together in ways that we didn't explicitly program. It is not enough to focus on what we directly tell these systems to do. We also have to pay attention to what behaviors might emerge when they interact with each other and with us. It's like raising teenagers. Sometimes the lessons they learn from their peers are more powerful than what you teach them directly. Now, if this video got your interest, I would encourage you to watch the video, The Dangerous Trust Crisis That AI Will Create, about the axial age. In it, I examine how the emergence of increasingly sophisticated AI behaviors, like the spontaneous cooperation that we just explored, is creating a fundamental trust problem in society. When AI systems can develop their own coordination strategies without human instruction, how do we know when to trust systems managing our information, like markets and social platforms? So the cooperation that's emerging between AI systems today isn't just changing algorithms, it's reshaping how we trust both our technology and each other. And if you're getting value from this episode, I would appreciate it if you would push the like button. Pressing like lets me know I'm making content you want to see, and it spreads that content to others. So thank you for supporting AI Capitalists.